flowchart. At the end of the lesson, you should be able to identify different kinds of technical drawing, interpret technical drawing, and prepare or make changes to electrical or electronic schematic and drawings. A flowchart is a commonly used by system analysts to visualize the series of processes in a business system. A flowchart is a useful tool to design an efficient business system and to troubleshoot or improve an existing system. Flowchart is a process of describing or showing the flow of operations that must be performed to solve a certain problem using different symbols. Flowchart is a visual or graphical representation of the data flow. A flowchart represents the whole thing that you can plan or do. The given flowchart below describe the simple actions. Flowchart shows the exact sequence of procedures to be made and describe the flow of data. It uses graphic symbols that represent as terminator, process, sub-process, decision, arrow lines, and connectors. The most commonly used flowchart symbols are the following. We have the terminal symbol, usually start and end. A flowchart used to start and end a process or an action. Remember, all flowchart has a beginning and end, and we use this capsule as a terminal symbol. Next, we have rectangle. It is used as a process. This is used to represent process, procedure, or any action taken. Rectangular with double lines on each side represent a sub-process. These may be subroutine procedure that divide into at any point of the process. So if the process is huge, if the process is general instruction, you may use the sub-process to detail the step-by-step procedure. Next, we have the rhomboid. It symbolizes data. This is used to show data or information that entering or leaving the process. This flowchart symbol usually used as input or output. So, whenever you want to view the result, view the answer, or enter a data, you will use the rhomboid. And lastly, we have directional arrow serve as connector lines to connect the different symbols, flow of action, and data from one symbol to another. The directional arrow give us the procedure on what step or the flow of the program. Procedures in creating flowchart. Making flowcharts are quite difficult. So when creating a flowchart, we must remember the following. What is the purpose? It should be described in a clear and definite process. Each procedure should be clearly presented. Always focus on the main flow. Provide useful conclusion to the entire process. The flow of the process should be from left to right, top to bottom. And lastly, write a brief and clear word or code inside the flowcharts. Basic flowcharting forms. There are 3 basic flowcharting forms. And number 1 is the sequential program flow. It is a simple arrangement of actions and process. It is composed of a series of statements which are executed one by one from top to bottom. So as you can see, we have the terminal start, then go to the library, and then borrow books. After borrowing books, you will read it. After reading, you will return the books, and that's the end. So this is a very clear, a simple instructions what to do when you go to the library. Next, we have the decision program flow. Involves a decision to determine the truth or falsify of a certain statement. The direction of the flow depends on the result of the decision. So, given an example, make a program. Is the decision okay? If yes, you print the decision. If not, go to end. So end the process. So here we use the rhomboid in to answer the question, is the program okay? Next we have, and lastly we have the looping program flow. Repeats an action for a number of times as initially set until a certain condition is met. Observe, we start with a terminal, then it goes to input password. After you input your password, is the password correct? So there is a decision where, which is answerable by yes or no. So is the password correct? If yes, where will you go? You proceed to the different application. However, if the password is incorrect, you go back to input password until you get the correct password. You will not stop encoding or typing the password until you get the correct password. And then, after processing the other application, it goes to end. For your learning task 1, answer the given jumbled letters below. Our clue, it is used to connect the different data and flow of action from one symbol to another. The correct answer, connector lines. It is a process of describing or showing the flow of action. The correct answer, flow charting. It is used to represent a process, procedure, or any action taken. The correct answer, process. It is used when the decision has to be made, requiring an answer yes or no, true or false, on or off. What is this? The correct answer, decision. It is a symbol used to show data or information that entering or leaving the process. The correct answer, rhomboid. It shows the exact sequence of procedure to be made and describe the flow of data. The correct answer, flowchart. It is a symbol used to represent a process. The correct answer, rectangle. It is a subroutine procedure that divides into at any point of the process. The correct answer, sub-process. It is used to start or end a process. The correct answer, terminal. And lastly, it is a small circle symbol designed as. The correct answer, connector. For your learning task 2, modify true or false. Analyze each statement, then write technical if the statement is true. If the statement is false, write the word that make it incorrect and then write the correct one on the space provided before each number. The direction of the flow depends on the result of the decision. Always focus on the sub-flow. The flow of the process should be from right to left, top to bottom. Okay, I will give you a minute to think of your answers. For number 1, the direction of the flow depends on the result of the decision. The correct answer is terminal. Always focus on the sub-flow. That is sub-main, not sub-flow. The flow of the process should be from left to right, top to bottom, right to left, and left to right. Next. Number 4, write a detailed and clear word or code inside the flowcharts. Number 5, sequential program flow is composed of a series of statements which are executed one by one from top to bottom. For number 4, it should be detailed to brief. From complex to simplify. Next, for number 5, we have technical. Did you get it all correct? Let's try it once again. The terminal symbol marks the start and end of the flow. Number 7, decision program flow involves a decision or test to determine the truth or falsity of a certain statement. And number 8, use connectors to ensure that the symbols are properly connected and that the flow continues. Let's try to answer number 6. Terminal symbol marks the start and end of the flowchart. True or false? The correct answer is true. It is technical. Okay. 7. Decision program flows involve a decision or test to determine the truth or falsity of a certain statement. The correct answer is still true, so that is technical. Next, number 8, use connectors to ensure that the symbols are properly connected and that the flow continues. That is still true, so that is technical. Did you get it all correct this time? If yes, congratulations. If not, let's try to answer once again, one more time. Number 9, only a single flow line should enter and leave a process symbol. And thus, number 10, write your code inside the symbol in briefest and clearest manner as possible. Let's try to answer number 9. Only a single flow line should enter and leave a process symbol. Is it true or false? So the correct answer is true. That is technical. Then last, what is the code? Or write the code inside the symbol in briefest and clearest manner as possible. That is still true, technical. Did you get it all correct this time? If yes, congratulations. You are now ready to take your online test. If not, go back to the lesson flowcharting and try to understand the lesson. Try to answer all the given exercises before you take the test. Electronic schematic symbol graphic symbol have been developed for describing the connectors and functions of such circuit and systems. So, the batteries are presented on a schematic with a pair of disproportionate parallel lines. This number of lines indicate the number of series cells in the battery. Always remember that the battery has positive and negative. But by the way, these are the symbols that we are going to use to describe a circuit or a system. So when you see the positive and negative symbol, that represent battery. Next, we have the switch. Switch can be represented in numerous ways in electronic schematics. So, if you see this kind of symbol, that is already switched off. But if it's intact to the line, it's parallel to the line, it is on. Capacitors are either polarized or not. A polarized capacitor is marked with a positive sign. It is important to distinguish between these two because the polarized capacitor needs to be placed correctly accordingly to the positive sign. So we have a series of capacitor. The first capacitor is standard. The second capacitor is polarized. So as you can see, the polarized has a positive sign. Then the third symbol, standard capacitor, and then the last symbol is another polarized capacitor which has a big positive sign. In this video,
hey there guys, Paul here from the engineeringmindset.com. In this video we're going to be looking at capacitors to learn how they work, where we use them and why they're important. Remember, electricity is dangerous and can be fatal. You should be qualified and competent to carry out any electrical work. Do not touch the terminals of a capacitor as it can cause an electric shock. So what is a capacitor? A capacitor stores electric charge. It's a little bit like a battery, except it stores energy in a different way. It can't store as much energy as a battery, although it can charge and release its energy much faster. This is very useful, and that's why you will find capacitors used in almost every circuit board. So how does a capacitor work? I want you to first think of a water pipe with water flowing through it. The water will continue to flow until we shut the valve. Then no water can flow. However, if after the valve we first let the water flow into a tank, then the tank will store some of the water, but we will continue to get water flowing out of the pipe. Now when we close the valve, water will stop pouring into the tank, but we still get a steady supply of water out until the tank empties. Once the tank is filled again, we can open and close the valve as many times as we like. As long as we do not completely empty the tank, we will get an uninterrupted supply of water out of the end of the pipe. So we can use a water tank to store water and smooth out interruptions to the supply. In electrical circuits, the capacitor acts as the water tank and stores energy. It can release this to smooth out interruptions to the supply. If we turned a simple circuit on and off very fast without the capacitor, then the light will flash. But if we connect a capacitor into the circuit, then the light will remain on during the interruptions, at least for a short duration, because the capacitor is now discharging and powering the circuit. Inside a basic capacitor, we have two conductive metal plates, which are typically made from aluminium or aluminum, and these will be separated by a dielectric insulating material such as ceramic. Dielectric means the material will polarize when in contact with an electric field, and we'll see what that means shortly. One side of the capacitor is connected to the positive side of the circuit, and the other side is connected to the negative. On the side of the capacitor, you will see a stripe and a symbol. This will indicate which side is the negative. If we were to connect a capacitor to a battery, the voltage will push the electrons from the negative terminal over to the capacitor. The electrons will build up on one plate of the capacitor, while the other plate in turn releases some electrons. The electrons can't pass through the capacitor because of the insulating material. Eventually, the capacitor is the same voltage as the battery and no more electrons will flow. There is now a build-up of electrons on one side. This means we have stored energy and we can release this when needed. Because there are more electrons on one side compared to the other, and electrons are negatively charged, this means we have one side which is negative and one side which is positive, so there is a difference in potential or a voltage difference between the two, and we can measure this with a multimeter. Voltage is like pressure. When we measure pressure, we're measuring the difference or potential difference between 2 points. If you imagine a pressurized water pipe We can see the pressure using a pressure gauge. The pressure gauge is comparing two different points also, the pressure inside the pipe compared to the atmospheric pressure outside the pipe. When the tank is empty, the gauge reads 0 because the pressure inside the tank is now equal to the pressure outside the tank, so the gauge has nothing to compare against. Both are the same pressure. The same with voltage. We're comparing the difference between 2 points. If we measure across a 1.5 volt battery, then we read a difference of 1.5 volts between each end. But if we measure the same end, then we read 0 because there's no difference, it's going to be the same. Coming back to the capacitor, we measure across and read a voltage difference between the two because of the build-up of electrons. We still get this reading even when we disconnect the battery. If you remember with magnets, opposites attract and pull towards each other. The same occurs with the build-up of negatively charged electrons. They are attracted to the positively charged particles of their atoms on the opposite plate. They can never reach each other because of the insulating material. This pull between the two sides is an electric field which holds electrons in place until another path is made. If we then place a small lamp into the circuit, a path now exists for the electrons to flow and reach the opposite side. So the electrons will flow through the lamp, powering it, and the electrons will reach the other side of the capacitor. This will only last a short duration though until the build-up of electrons equalizes on each side. Then the voltage is 0, so there is no pushing force and no electrons will flow. Once we connect the battery again, the capacitor will begin to charge. This allows us to interrupt the power supply and the capacitor will provide power during these interruptions. So where do we use capacitors? They look a little bit different, but they're easy to spot. In circuit boards, they tend to look something like this, and we see them represented in engineering drawings with symbols like these. We can also get larger capacitors, which are used, for example, on induction motors, ceiling fans, and air conditioning units. We can get even larger ones, which are used to create poor power factor in large buildings. On the side of the capacitor, we will find two values. These are the capacitance and the voltage. We measure capacitance of the capacitor in the unit of farads, which we show with a capital F, although we will usually measure a capacitor in microfarads. With microfarads, we just have a symbol before this, which looks something like a letter U with a tail. The other value is our voltage, which we measure in volts with a capital V. On the capacitor, the voltage value is the maximum voltage which the capacitor can handle. We've covered voltage in detail in a separate video, do check that out, links down below. As I said, the capacitor is rated to handle a certain voltage. If we were to exceed this, then the capacitor will explode. Let's have a look at that in slow motion. Pretty cool. So why do we use capacitors? One of the most common applications of capacitors in large buildings is for power factor correction. When too many inductive loads are placed into a circuit, the current and the voltage waveforms will fall out of sync with each other, and the current will lag behind the voltage. We then use capacitor banks to counteract this and bring the two back into alignment. We've covered power factor before in great detail, do check that out, links down below. Another very common application is to smooth out peaks when converting AC to DC power. When we use a full bridge rectifier, the AC sine wave is flipped to make the negative cycle flow in a positive direction. This will trick the circuit into thinking it's getting direct current, but one of the problems with this method is the gaps in between the peaks. But, as we saw earlier, we can use a capacitor to release energy into the circuit during these interruptions, and that will smooth the power supply out to look more like a DC supply. We can measure the capacitance and the stored voltage using a multimeter. Not all multimeters have the capacitance function, but I'll leave a link down below for the model which I personally use. You should be very careful with capacitors, as we now know they store energy and can hold high voltage values for a long time even when disconnected from a circuit. To check the voltage, we switch to DC voltage on our meter, and then we connect the red wire to the positive side of the capacitor and the black wire to the negative side. If we get a reading of several volts or more, then we should discharge that by safely connecting the terminals to a resistor and continue to read the voltage. We want to make sure that it's reduced down into the millivolts range before handling it, else we might get a shock. To measure the capacitance, we simply switch the meter to the capacitor function. We connect the red wire to the positive side and the black wire to the negative side. After a short delay, the meter will give us a reading. We will probably get a reading close to the stated value, but not exact. For example, this one is rated at 1000 microfarads, but when we read it, we get a measurement of around 946. This one is rated at 33 microfarads, but when we measure it, we get around 36.
Resistor reduces current flow. The symbol is often drawn as a resistor with an arrow across it or pointing down on it as it one below. So we have American style and the European style. So when you see this type of resistor, you know if it is American style or European style. Next, we have variable resistor or potentiometer as drawn in several different ways. Transistor is like an electronic switch. It can turn a current on or off. The most common transistor types are the field effect transistor and the bipolar junction transistor. Notice the difference between the two types of transistor. In field effect transistor, it's going in to the system, while the bipolar junction transistor, it's going out of the system. Next, we have the diode. Family has several different symbols because there are several different types of diodes. We have the standard diode, Zener diode, and light emitting diode. The induction is also called a coil or reactor. The coil stores energy in a magnetic field or flux. An inductor symbol looks like a coiled wire, as it is what an inductor essentially is. Next, we have the transformer. Transformer is two or more coils coupled by magnetic induction. It helps keep the frequency and reduce tension in an AC circuit. The symbol of the transformer looks like two inductors with something in between them. So, transformer, two or more coil, while the induction only a coil, just to store energy. The next symbol is known as the integrated circuit or IC, are usually shown as rectangular boxes with pin names. So notice that each pin has different name. The first pin is GND, I'm sorry. GND. The second pin is TR. Third pin is Q. Fourth pin is R. The fifth pin is CV. Sixth pin is THR. And the seventh pin is DIS. So that is integrated circuit. There are several different pins and each pin has its own name. Drawing schematic diagram. A well-diagrammed schematic makes it easy to understand how a circuit works and aid in troubleshooting. A poor schematic only creates confusion. By keeping a few rules and suggestions in mind, you can draw a good schematic in no more time than it takes to draw a poor one. Here is an example of a DC power supply schematic diagram. So, do you understand the diagram given? It says here it has 120 with a 60 kilohertz. Okay? So, we use, what is this two coil? Transformer. Do you still remember? The two coil here is the transformer. Do you still recognize this diagram? Okay, we have here the resistor and the volt. So all the diagrams given here are already in our lesson. Okay? So all you have to do is to remember all the symbols given. Purpose of technical drawing. The purpose of technical drawing is to clarify an idea or to translate that idea into a common graphical language. Technical drawings fulfill the purpose of idea translation through the application of a variety of methods and visual conventions. So that is the purpose of drawing. To make things easy to understand and to visualize what is the flow of that diagram. Store technical drawings and equipment or instruments. It is important that the equipment which has been in use is stored neatly in clean and dry place. Dirty and damaged equipment does not help in production of good and clean drawing. The proper care and maintenance. Number 1, avoid dropping your tools and equipment. Number 2, never use measuring tool in cutting paper. Number 3, do not sharpen your pencils on top of your workplace. Number 4, wipe off the surface and edge of triangles and T-squares. Number 5, sharpen and store your pencils properly after use. 6, find or create and organize where you can hang your measuring tools. 7, have a separate container for marking tools. 8, keep your drawing sheets in a plastic tube to protect them from dust and dirt. 9, never lend or borrow drafting tools and materials if may. And lastly, always clean the instrument and the drawing table before beginning your work. For your learning task 4, on a piece of paper, write your understanding about the purpose and the importance of schematic diagram in electronics. Does it make sense to you? Just try to write at least 3 sentences about the importance of a schematic diagram in electronics. Okay, to be submitted in your Google Classroom. That's all for today. Goodbye, class.